Welcome back, Focus Learners. Okay, so today we are pulling out the magnifying glass and stepping right inside the microscopic factories that power human biology. This explainer is all about the micromechanics of enzymes and exactly how they survive in what we call the biological Goldilocks zone. Let's dive in.
So what exactly is the body's Goldilocks zone? You know, it's crazy to think about, but just a tiny shift in your internal temperature, literally just a few degrees, can bring your body's machinery to a complete and total standstill. It's absolutely true. Just like Goldilocks needing her porridge not too hot and not too cold, your body's enzymes demand a perfectly balanced environment to function. Why does a slight fever or a random drop in body temperature have such a catastrophic system-wide effect? Let's figure it out.
Here's our roadmap for this explainer. First, we'll enter the biological factory. Then we'll cover lowering activation energy, the lock and key, the Goldilocks zone, the denaturation disaster, and we'll wrap it all up with your exam success blueprint.
Section 1. The biological factory. Let's meet our tiny microscopic workers.
Right, so what actually is an enzyme? Simply put, it's a biological catalyst, almost always a protein, and its main job is to speed up chemical reactions in the body without ever being used up itself. Look at that magnified view zooming in on the micro level right now. See those vector arrows? They're tracking those little geometric molecules as they move straight toward that coiled-up enzyme structure. It's kind of like watching tiny, indestructible factory workers just tirelessly assembling and breaking down molecules to keep you alive. Pretty wild, right?
Moving on to Section 2, lowering activation energy.
Okay, so every single chemical reaction needs a little push to get going. We call that activation energy. Check out step 1 in this sequence. See that massive hill? That's the high activation energy of an uncatalyzed reaction. Imagine a skateboarder trying to push up and over that massive peak. It takes a ton of effort. But now watch step 2 as the enzyme enters the picture. And boom, in step 3, follow that red downward arrow. See how the dimension line for the energy requirement literally shrinks right before your eyes? That is the enzyme lowering the activation energy. It's basically building a ramp for our skateboarder, so the reaction happens super easily at our normal body temperature.
Section 3. The lock and key. This is where enzyme specificity really comes into play.
This is such a cool way to picture structural specificity. See that large blue structure labeled enzyme? These guys usually end in ASE, like protease for breaking down proteins. Now, look closely at that jagged groove cut right into the top of it. That is the active site, and hovering just above it with those arrows pushing it down is the smaller substrate. It's exactly like a physical lock and key. The substrate has to fit perfectly into the enzyme's groove. If the shapes don't match exactly, well, the reaction just doesn't happen. No way around it. Each enzyme is a total specialist. It only ever acts on its one specific target.
All right, Section 4, the Goldilocks zone. Let's look at the precise environmental conditions these microscopic locks and keys actually need to work.
Now, here is the absolutely crucial number, 37 degrees Celsius. Notice how that dynamic thermometer scale rests perfectly right there in the green middle zone? Enzymes are ridiculously sensitive to temperature. They have an optimum temperature, where they hit absolute peak performance. For most human enzymes, this sweet spot is exactly 37 degrees Celsius, our average body temperature. It's the perfect balance, giving them enough kinetic energy to move without destroying their structural integrity.
Let's break down exactly how this balance works. Scanning across the top row here. At low temperatures, kinetic energy is super low. Those visual indicators show practically zero collisions between our lock and key. The enzyme status? Totally inactive. It's basically on pause. But drop down to that bottom row. At our 37-degree optimum, the kinetic energy column shifts to high. We're talking frequent, rapid collisions between substrates and enzymes, which means optimum activity. The heat literally provides the movement needed to make this biological factory hum along.
Section 5. The denaturation disaster. Let's see what happens when we push things way past 37 degrees.
Trace this curve right across the chart with me. That first bar, low activity when it's cold. Then, as the temperature rises, activity peaks right there at the 37-degree maximum bar. But look really closely at what happens next. The activity doesn't just taper off gently. Follow that downward arrow as it literally crashes to zero. When it gets too hot, as you can see with that fire icon and those broken molecules, the enzyme undergoes a total structural collapse.
Now, this split view clears up one of the most common misconceptions out there.
On the left, we've got the enzyme labeled inactive from being too cold, totally frozen by those ice crystals. But remember, this is just a temporary pause. Warm it back up, and it's good to go. But check out the right side, labeled denatured because it's too hot, completely surrounded by flames and red lightning bolts. That active site is irreversibly altered. People often say the heat killed the enzyme, but actually, scratch that. It's a protein. It wasn't alive in the first place. What actually happened is its shape got permanently deformed. It's like taking a physical metal key and bending it with pliers. No matter what you do, it is never fitting into that lock again.
And hey, temperature is not the only culprit here. See that warning triangle and the bubbling beaker? Extreme pH levels, like those highly acidic drops falling from the pipette labeled pH 2, have the exact same destructive effect. Every single enzyme has a very specific pH range it can tolerate. If you cross that boundary marker, the extreme acidity or alkalinity will irreversibly denature the enzyme. It completely shreds that precise active site shape we looked at earlier.
Section 6, the exam success blueprint. Get your mental notepads ready.
All right, here is your quick-fire checklist. What exactly are enzymes? They're biological protein catalysts. What's their main mechanical job? They lower activation energy. How do they bind? Through that highly specific lock and key action. What do they absolutely rely on? An optimum temperature and pH. And finally, what happens when conditions get extreme? Denaturation, which is an irreversible structural change.
If you want to absolutely crush your exams, you've got to commit this rule to memory. Always consider conditions of temperature and pH. Relate your answers to the enzyme's optimum conditions to score full marks. Seriously, if a question asks why a reaction stopped, do not just write the enzyme died. No way! You have to explicitly say that the conditions exceeded the optimum temperature or pH, which led to an irreversibly denatured active site. That exact level of precision is what examiners are hunting for.
So I'm going to leave you with one final thought to chew on. We've just seen how incredibly delicate our internal biological factory really is, completely reliant on that 37-degree Goldilocks zone. But if human enzymes are perfectly adapted to our internal temperature, what about organisms living in boiling volcanic geysers or freezing subglacial lakes? What kind of extremophile environments are out there right now, holding totally unique, indestructible enzymes that could trigger the next massive biological or industrial revolution? It's a pretty wild puzzle to think about, right? Keep visualizing those mechanics, keep questioning the variables, and I'll catch you in the next explainer.